Hey folks, in this video I'm going to demonstrate the uniaxial tension test, and I'm going to be doing it on a ductile material. So the uniaxial tension test is governed by ASTM standard E8 and E8M, and the ASTM standard specifies everything from the specimen geometry and how the specimen has to be prepared, the testing equipment that must be used and the properties that it must have, the test parameters, and also the conditions that have to be met for the test in order for the test to be considered a valid test. And the purpose of all these specifications is first to remove potential sources of error in the test, and also to make sure that engineers everywhere agree on exactly what they mean when they report standard mechanical properties like the Young's modulus, the yield strength, and the ultimate tensile strength. Okay, so I'm going to go ahead and prepare my specimen geometry now. All right, I've prepared my specimen for testing. So you can see that I've got this long, thin section in the middle. This is called the gauge length of the specimen. And then I've got these wide, flat areas at the top and bottom that I'm going to be using to grip on the machines. And I've done my best to also make sure that the edges of this gauge length are fairly smooth so that we don't have any sharp edges that could serve as potential initiators for cracks. Of course, ASTM standard doesn't specify what you do with the scraps, so leave that up to the engineer's judgment. Next thing we have to do is to measure the dimensions of our specimen. So since we're going to be computing stress and strain, two things we need to know are the original cross-sectional area and the original gauge length. So first, to get the cross-sectional area, let me get the width of the specimen. It comes out to about 3.6 millimeters. I'm sorry, the thickness. And now let's measure the width. The width of my specimen is about 14.4 millimeters. Now, for measuring the gauge length, I first need to attach the device that's going to measure the extension of my sample. So here's my extensometer, and you can see it's got two little flexible arms here that are going to attach onto my specimen. So let me go ahead and attach those now. All right, I've attached my extensometer. Now, a real extensometer would have little strain gauges on these flexible arms here, and that's what would be measuring the actual change in length of this extensometer. So this is the gauge length over which we'll be measuring the change in length. So that's the distance that I need to know in order to compute the strain. So I'm just going to go measure between the centers of these two little connection points, and that's about 39 millimeters. So that's going to be our gauge length for the purposes of computing strain. Okay, let me go ahead and get my sample situated in my test fixture. All right, I've got the sample situated in the test fixture. You can see it's been clamped down here at the bottom. And a tensile testing machine needs to have a load cell in order to measure the force. So normally the load cell would be on top of the sample on the part of the machine that moves. That's the typical setup, but it's also common to see the load cell on the bottom. In this case, I'm using a scale for my load cell, so I'm going to be measuring the load from the bottom. So I'm going to go ahead and begin the test now. Oh, shoot. So because our sample fractured outside of the gauge length, this would not be considered a valid ASTM test. So I'm going to go ahead and dispose of the specimen in an appropriate manner and get a new one ready for you. Okay, I've gone ahead and prepared a new sample here. So let's see if we can end up with a valid test this time. So I'm going to go ahead and start performing the test. You can see the length inside the gauge length is increasing. That's where most of our strain is. Oh, it looks like we're starting to form a neck. And eventually that neck is going to pinch off, and there we have our fracture right inside the gauge length. So that time we got a valid test. All right, after the test is finished, there's a few more properties that you can measure by looking at the broken specimen. So here we have the two pieces of our specimen. And the first thing that we want to measure is the percent reduction in area. So if we look at the original specimen, the gauge length was approximately this wide, and this is what our specimen looks like now. So we can compare the new dimensions of the specimen, and it's narrowed down to about 6 millimeters wide and 3.3 millimeters thick. So the percent reduction in cross-sectional area tells us something about the ductility of the material. Another measure of ductility that we can use is to actually fit the pieces, the broken pieces back together. You have to be kind of careful here to line up the fracture surfaces. And then measure the total length, the total gauge length after fracture. And that gives you the elongation after fracture, and that's another measure of the ductility of the material. All right, that's all for this video. I hope you enjoyed it, and I really look forward to seeing what tests you folks come up with. Thank you.